Okay, hello students, welcome back. This is 2.1 and 2.2. We're going to describe and graph quantitative variables. That means that we're going to talk about something called a histogram in this one. Okay, let's go over our objectives today. Objective is to be able to create by hand and using technology and interpret histograms. So keyword is histograms of quantitative data. That just means numbers, numerical data. Be able to create by hand and using technology and interpret dot plots and stem and leaf plots. Be able to describe the shape, center, and spread of a distribution of quantitative data. And be able to interpret the shape of a histogram and describe its behavior in the distribution of a distribution in context. Okay, describing distributions of quantitative variable. When asked to describe a distribution, you must be able to describe the following clearly, and it's SOX. So what does SOX stand for? Well, SOX stands for the shape, the center, and the spread. Okay, the O does not stand for anything. It's just there to give us a mnemonic device. SOX, SCS, shape, center, and spread. So the shape, we'll get into the different types of shapes today. You could have a flat shape. You could have one that's curved. Okay, you could have multiple curves. Okay, that's the shape. The center, where's the center or the balancing point? I like to think of it as the balancing point of the graph. Okay, if I were to balance the graph on this is called a fulcrum, okay, or a pivot. Okay, what would that look like? And where would it be located? Where would the balancing point be located? And the spread, is our data spread out or is it bunched together? Okay, is the data spread out or is it bunched together? So the shape, the center, and the spread. Okay, refresher, let's create a frequency table because that's going to lead us into building our first histogram. Okay, complete the frequency table from, these are the GPAs that we saw last time. So for 1.0 to 1.1, how many GPAs were there? Well, looks like there were 2 of them. Okay. For 2.0 to 2.9, looks like there are 6 of those. 3.0 to 3.9, looks like 7 total there. And 4.0 to 4.9, looks like there's just 1 there. And this was 16 total. So the relative frequency here is 2 out of 16, or 1/8, 6 out of 16, or 3/8, 7 out of 16, that doesn't reduce, and 1 out of 16. Okay, so let's use this information to build our first histogram. A histogram can be built based on the relative frequencies here. So I'm going to take this, or sorry, not the relative frequencies, just the frequencies. I'm going to take the frequency column. Okay, we could do a histogram based on the relative frequencies as well, but we're just going to start with the frequency column, and we're going to do a histogram with respect to the frequency. Okay, so we want to do a visual representation of this data. So the highest frequency is 7. So on the y-axis, I'm going to go up to 7. So 1, 2, 3, 4, 5, 6, and 7. So 1, 2, 3, 4, 5, 6, and 7. Okay, on the y-axis. Okay. And then on the x-axis, I'm going to go from, well, I don't have any, I'm going to start at 0, but I don't have anything from 0 to 1. So I'm going to start here at 1.0. Okay, and then we're going to go to that's going to go to 1.0. So the next one is going to be 2.0. Okay, so 1.0 to 1.9 will be contained in this first column. We're going to create a column now that represents all the data from 1.0 to 2.0. Okay, so 1.0 are basically 1.9 because 2.0, remember, is in the next bin. These are bins, right? So how many are in the first bin? That's 2. So I'm going to go up to 2 and draw a line, and I might write a 2 on the top there and say, hey, you know what? That is 2. That represents all the data, how many pieces of data that I have between 1.0 and 1.9. Okay, what about from 2.0 to 3.0, not including 3.0? Well, that's 6. So now I'm going to go up to 6, draw a line at 6, and I'm going to say, oh, okay, this goes from 2.0 all the way to 3.0. That's 6. Okay, and that's my next column. What about the next one? Well, that one goes up to 7. So from 3.0 to 4.0, that's going to go up to 7 here. Okay, so a little higher than 6. And that gives me 7 there for that column there. Okay, and then what about 4.0 and higher? I'll put a 5.0 there. There's only 1, so that's way down here on 1. And there we go. And there's our first histogram. So, okay, way to go. Okay, draw a histogram with bin size 5. Okay, and the first bin starting at 10 for the following ages of people. Okay, so this is in order. Okay, so we want our bin size to be 5, and it's going to start at 10. So I want to figure out, okay, so if we're going to go up 10, 15, 20, okay, so how many items are between 10 and 15? Well, that's going to be 10, 11, 12, 13, and 14. I'm not going to get to 15 though, because that's in the next bin. So it's everything less than 15 will be in the first bin, and that's 2. What about the next bin? Well, that's going to be 15 through 19. Okay, we're not going to include 20 in our next bin. And this will be 20 to 24. We're not going to hit 25. Okay, and then 25 to 29, the last one here, the next one here, and then 30 to 35, or sorry, 30 to 34. And so we get 1, 2, 3, 4, 5 bins. Okay, and so we're gonna look at those. So we're gonna start where we're gonna start. We're gonna start at 10. So if we wanted to kind of space it out evenly, we'd go 0, and then 5, and then 10, right? And then 15, 20, 25, 30, and 35, and I would stop there. Okay, so what are the frequencies here? Well, there's 2 items between 10 and 15. There's 1, 2, 3, 4, 5 items between 15 and 20. There's 1, 2, 3, 4, 5, 6, 7 items between 20 and 25. There's 3 items between 25 and 30, and there's 2 items between 30 and 35. Okay, so there's nothing between 0 and 5, and there's nothing between 5 and 10. So the highest again is 7. So I'm going to go up to 7 here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'm going to widen this so I can draw a little easier there. Okay, so from 10 to 15, I'm only going to include the 10 and the 12. So that goes up to 2. So I'm going to draw a line at 2. Okay, and go over. And this is 2. And I'm going to put my 2 there on top. 15 to 20, that's 5 items. So let's draw a line at 5. Just kind of eyeball it. And we go down. Okay, 15 to 20. and that's 5 there. Okay, 20 to 25. Okay, so this is up to 7. Okay, 20 to 25. And we get 7. And then 25 to 30, that's going to be 3. So down to 3. And then 30 to 31, again, is back to 2. Oh, that's a 3. And then back to 2. Okay, so again, another nice histogram there. Okay. Okay. Data was collected for a sample of organic snacks. The amount of sugar in milligrams in each snack is summarized in the histogram below. How many snacks are represented in the histogram? Well, we'd have to add up all the columns here. The first column is at 4. The next column is at 5. The next column is at 10. Looks like this next column is at 13. Oops, I'll put it above it. 13. The next column is at 8. The second to last column is at 5 again. And the last column is at 2. Okay. So we want to add all this up. So we could go to a calculator if we wanted to. Add up, 4 plus 5 plus 10 plus 13 plus 8 plus 5 plus 2. And I get 47. So the total number of snacks represented is 47. How many snacks had more than 200 milligrams of sugar, more than 200? So that would be the 8, the 5, and the 2 here would be more than. So if I add up 8, 5, and 2, I get 15. So 15 snacks. How many snacks had between 170 and 220? Between 170 and 220. Okay, well, the way that I'm going to do this, I'm going to do a little sneaky. I'm going to say, well, which ones weren't included? Right? I know that there's a total of 47. So if I take 47 and I subtract off 4 and I subtract off 2, I should be left with 47 minus 4, which is 43, minus 2 is 41. So there's 41 that were in the middle here. Okay, what percentage of snacks had more than 200? Okay, so what percentage of snacks had more? Well, we already know that the number that's more than 200 here is 15. So we are going to do 15 divided by 47. And let's pull out the calculator again. So 15 divided by 47, 15 divided by 47 is equal to 0.319, looks like it's approximately 0.319. To change that decimal to a percentage, I would move the decimal over twice, and that's about 31.9%. Okay. We'll box these answers as well. Okay, let's talk about the shape, right? This is what goes back to the shape, the center, and the spread. Okay, we're not going to talk about the center and the spread just yet, but we will talk about the shape right now. So if it's uniform, that means that it's the same height throughout. Okay, uniform means that it has the same height throughout my histogram. So same height for everything. It's flat. Oops. Go back here. It is flat across. Okay, for all values, they are the same. Okay, that's what means uniform. Okay, so it's flat. Okay, symmetric. What does it mean by symmetric? Well, if I have a one that goes up, okay, it means that the right side is roughly identical to the left side. Okay, it's symmetric. Okay, we call it kind of like a bell-shaped curve. Okay, it's symmetric. Okay, so we call it a bell-shaped curve because a bell in olden days looked like this. Okay, had a little, okay, like that, and there was a little piece of metal that hung down. Okay, and here was the handle, and here was what was called the clapper inside the bell, boom, boom, boom. And so the shape, okay, we call that a bell curve. It's a bell curve of the shape. I'll put the shape in green that we're talking about here. It's this bell, the outside of the bell. Okay. Bell shaped, symmetric. It's a symmetric shape. Okay, what does it mean to be skewed left? Okay, or negative skew. Okay, skewed left, or we say that this is left tailed. It has a tail. Think of it like a dinosaur, right? Which way is the dinosaur facing? Okay, so if I drew a little dinosaur here, okay, and we want the tail on the left, then the tail would go up like this, right? And then I'd have my little dinosaur guy. Okay, I don't know how they would look. Okay, but whatever. This I'm such a bad artist. Don't even. This is just not okay. But his tail, okay, would be on the left. The dinosaur would be facing to the right. The tail would be on the left. Okay. There. And so if it's left-tailed, okay, then it means that we start low and we end high. We start low with our distribution and we end high, and so we get a tail here. Okay, this is called left-tailed or left skewed or skewed left. Okay. Okay, what about skewed right, or what we call right-tailed? Okay, well, that's just the opposite. It means that the dinosaur tail would be going to the right. And so we would start high, okay, and we would end low. And so this is right-tailed or right-skewed. Okay, unimodal means that we have one bump. Okay, one bump, unimodal. So what would this look like for a histogram? Well, we could, oops, we have one hump here, or one bump. Okay, and so we say that's unimodal. It doesn't have to be symmetric. We could, you know, it just has to have one significant, what we call mode. Okay, one that occurs the most. Okay, so this is unimodal, one bump. What about bimodal? Bimodal means two. Okay, two bumps. So this is going to be two bumps. So maybe we start out like this and we go down again, but then we end up going up again, and then we peter off. So we can see that we went up, down, and so we get two bumps. Okay, two bumps there. Okay, other features that you might notice if there's clusters or gaps. Okay, so meaning that. Okay, so we could get a cluster of information. Okay, some over here, and then nothing in the middle, and then maybe some more over there. Okay, so say that we Okay, we get cluster here and a cluster there, and there's nothing in between them. It means basically that we have two different types of data sets, and we just ended up combining them. The data tells us there's two separate populations there, and they may have different features. Okay, what's an outlier? Outlier is one that does not fit the rest of the group. And so we can have outliers that are really low, or we can have outliers that are really high. I'm going to draw one that's really high. And so we get, an outlier way out there, and so he's kind of the oddball. Okay, that's the outlier. Okay, let's draw some examples of, what this would look like. Okay, number of miles run by Saturday morning joggers at a park. Okay, draw and describe the shapes of the distribution that might be found for each situation. Okay, number of miles run Saturday morning joggers at a park. So let's just kind of come up with, the scenario. Okay, when I go out to jog, I'll probably do like 2 or 3 miles, and then that's it. Okay, do like around 5K, and I'm done. Right, and then so maybe we could have like, people that did 0 to 1, 1 to 2 miles, 3 miles, 4 miles, 5 miles, 6 miles, 7 miles. I mean, we could go 8, 9. I'm going to stop at 10, because if you're running around a park and you do 10 miles, that's a lot. Okay, so maybe we have like, a few people doing less than a mile. Maybe a bunch of people do 1 to 2 miles. A few, or maybe the same amount of people do 2 to 3 miles, 3 to 4. Maybe we wouldn't even have anybody doing 4 to 5. And then there's these wacko people that are out here doing maybe 8 to 9 or 9 to 10. These are your outliers. Okay, those are the people that are, training for some sort of, marathon or something. Okay, number 2, hours spent by US adults watching football on Thanksgiving Day. Well, this again, we could have, a bunch of people that, maybe don't watch any football, 0. Okay, so, and then how about maybe from 0 to 1, or less than 1 hour, a few people. Okay, maybe a few more from 1 to 2 hours. Okay, we'll have maybe a few more, and then 2 to 3. Now, I don't know about you, but if I'm already invested in 2 hours of a football game, I probably will just want to watch it to the end. So maybe a few low people will do 2 to 3 hours. And then usually a football game is like 4 hours. So I'm going to say that majority of people who are watching it might complete the game from 3 to 4 hours. Okay, so maybe something like that. Okay, so what do we notice here? Well, we know that we're getting many modes, many bumps there. And so we could say that this is multimodal. Okay, I don't know if it's not really bimodal, it has more than one bump there. So I'm just going to call that multimodal. Okay. Okay, amount of winnings of all people playing a particular state's lottery last week. Okay, amounts of winnings. Okay, so again, maybe a bunch of people won nothing, 0. Maybe a few people won like, $50 or something, or $100, 50 to 100. Maybe even a fewer people won, 100 to like $1,000, and then probably not much you know, and then there's like this one person that wins the jackpot, right? So out there. So again, this guy that wins the jackpot would be the outlier. Okay, so outlier. It would also be skewed right. So keep in mind that this thing is going to be skewed right. Why? Because as the prize awards go up, okay, as the prize awards go up, the number of people that would win those would be going down. Okay, so this is definitely skewed right. And this outlier probably wouldn't even look like that. It would be like, you know, in the grand scheme of things, it would be like a tiny little bump. Okay, that's the winner of the jackpot. Okay, ages of faculty at your school. Okay, so ages of faculty at your school, the ages of the professors at your school here. What would that be? Well, let's say that you know, you probably aren't going to be hired to teach if you're less than 20. So we'll start at 20, and then 30, and then 40, and then 50, and then 60, and then 70. Okay. Should I put 80 there? Maybe 80. We'll stop at 80. Okay, we'll assume that most people are retired by 80. Okay, although there was a guy that was like, I don't know if he was teaching, but he was tutoring until he was like 91 or 92. It's craziness. Okay, so so at 20, maybe those between 20 to 30, we'll have that be a bin. 20 to 30, you're just starting out. Maybe we have a few of those. Okay, 30 to 40, more of those. 40 to 50, maybe the majority of people are teaching between 40 to 50. Okay, maybe 50 to 60 is the same. Maybe that's like the real bulk of it is, you know, your 40 to 60-year-old range. And then it goes down from there, 60 to 70, and then 70 to 80. So what would you say about this one? I would say this is unimodal and fairly symmetric. Okay, so that's unimodal and fairly symmetric. Okay, last digit of a phone number on campus. If you took and you just randomly ask people, what's the last digit of your phone number? I would say that you would probably get something called a uniform distribution. Okay, you take your digits 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And roughly, because it's just by chance that you would get any of these digits to be the last number of your phone number, I would say that it would be pretty evenly distributed. Okay, so it's we're going to call that a uniform distribution. Okay, and scores on an easy test, in an honors math class. Scores of an easy test. So we've got smart people taking an easy test. I'm going to say that, and the scores, maybe we'll start at 50, 60, 70, 80, 90, and 100, right? 100 plus, okay? And so maybe not many people do 50 to 60, more people 60 to 70, 70 to 80, 80 to 90, and 90 to 100. Okay, and so yeah, what's this? This is going to be left-tailed or left skewed. Okay, so skewed left. Okay, tail of the dinosaur. Okay, there's the dinosaur tail. Tail of the dinosaur is on the left. Okay, describe the following distributions. Okay, shape, center, and spread. Researchers collected data on a mother's IQ of 36 randomly sampled gifted children. Okay, so what does this look? What's the shape? The shape, I'm going to say that that's pretty symmetric. I'm going to say that it's also unimodal. Okay, and it could be even, you know, kind of like a bell shape. Okay, bell-shaped curve. Okay, what about the center? The center, where's the balancing point on this? If I were to put the balancing point, where would it be? Well, it would be probably somewhere between 115. Okay, if I were to balance all the data here, it would be somewhere between 115 and 120. Between 115 and 120, right in the center there of all of that data. 15 and 120. Okay, and then what's the spread? What's the spread? What's the range of this data? Well, it goes all the way from 100 to 135. So 100 to 135. So it's spread. The spread is 100 to 135, and we call that the range. Okay, so this is the range. Okay, distribution of numbers of characters used from for 50 emails is given below. Okay, so not a lot, and then we go down and there's a bulk of people who are writing very long emails, and then some people that are just writing books, I guess. Those are my outliers, right? So this outlier. Those are the people that are writing books there. Okay, what else do we notice? Well, we kind of notice that it in a way it is bimodal. Okay, so it's kind of bimodal, but it's also skewed right. Okay, it's skewed right. Okay. And so let's talk about that. So shape, okay, is skewed right. Okay, maybe bimodal. Okay, there's an outlier. Exists. Okay. What about the center here? Where do you think the center would be located? Well, we have a lot of the data pushed more toward the left of the graph, right? So our center is going to be shifted more to the left. So I would even say that the center would be, you know, maybe even right here at 10. Okay, it'd be somewhere around 10. If I wanted to balance this, you know, think of it on a balance, maybe right around 10 there. So I'm just going to put around 10. Okay, and the spread, what's the spread here? Okay, we have a range from 0 to looks like 65. Okay, that's our range. Okay, in section 2.3 to 2.5, we'll study more ways of describing the center and the spread with more precision and calculation. Okay. Okay, so what are other ways to graphically represent data other than a histogram? Okay, well, for categorical variables, there's pie graphs, there's bar graphs, which is, this is like a histogram. Okay, but the bars don't touch, okay, because they're categories. We can't, and you can't really rank them. Now, if you do rank a bar graph, then it's called a Pareto chart. And this is a ranked bar graph. Okay, so if you put things in order from highest to lowest, this is like a histogram. And a pie chart, hopefully everybody's seen a pie chart. Okay, we just put it into pieces and it is the percentages. Okay, and then segmented bar graphs. Okay, we can, you know, put them in segments, or we can have, you know, multiple bar graphs together comparing two different populations, right? So maybe we had like one bar graph, one bar, and then another bar, and then another bar. And then we put two items next to each other from different populations. This is maybe if you asked, men, what's their favorite color, you would get the red. And then if you asked women what their favorite color is, you would get the green. And so you could have multiple bars comparing different items. Okay, what about quantitative variables? These are your numbers, right? You're like 1.5s and 1.2s. So we get a histogram, we can do a dot plot, right? So a dot plot, dot, 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 dot. Okay, instead of the histogram with the columns, we just put a dot at the top. And then for a line plot, we connect the dots with lines. Frequency polygon, we're not really going to get into that too much. Stem plot, we'll talk about that, and a box and whisker plot, talk about that too. Okay, and time series, we're not going to get into that either. Okay, so the following is a list of 8 IQ scores. Okay, let's put in order for us. Let's do a line plot / dot plot. Okay, so let's do the dot plot, and then we're going to connect it with the lines. Okay, so what a dot plot is basically a histogram with dots. Okay, that's a dot plot. That's it. It's a histogram with dots. So let's look at our histogram here. So we're going to go, we have 87, 89, 96. So basically the range is 87 to 103. Okay, so let's see what we can do here. So 87, 88, 89, 90. Can we go all the way to 103? 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101. I think I'm going to go off the page here. 101, 102, and 103. Okay, so now for each of these values, I'm going to put a dot. Okay, so 87 has 2 dots. Okay, 89 has 1 dot. Okay, 96 has 2 dots. Okay, 101 has 1 dot, and 103 has 2 dots. Okay, so there's my dot plot. Okay, if I want to do a line plot, I could then connect the top dots together. I could say, maybe I'll use a ruler for this. Okay. I could connect these dots together. So let me connect that. Okay, oops, I'm a little bit too far on that one. Okay. Dot to dot. Okay, and then we're going to go to the next one. Oops. Okay. Just perfect. Okay, dot to dot. Okay, and then down. Like so. And then this one. And these are actually really easy to build in Excel. Okay, spreadsheet. And you say, oh, I just want a line plot. And you're like, oh, okay, cool. Okay. This is a histogram. The dot plot is a histogram with dots. Okay, and then the line plot on top of that is the top. What about a stem and leaf plot? Okay, a stem and leaf plot. The stem represents, okay, in this case, it will represent the tens place of, the decimal, and the leaf will represent the ones. Okay, the tens place and the ones place. So let's go tens place and the ones place. So we're going to organize these, and we're going to say, okay, so the first one is 87. So the 10 there is 8 and then a 7. And then I'm going to get 87 again. Well, I don't rewrite the 8, but I do write another 7. And so this represents 87 and 87. The tens is 8, and then we have 87, 87. And then we're going to put a 9 there for 89. That represents 89. What about 96? Well, that's a 9, and then we've got 96 once and 96 again. Now, what about 101? That's 10 tens is 100. 10 tens is 100. So this is going to be 101, 103, and 103. Okay. Let's talk about what a back-to-back stem and leaf plot is. Okay. So we can do a stem and leaf plot based on two different things, comparing two different items here. Okay. Each of them is going to be, this is the ones place, basically. This is the ones place. And each of them is going to be the tenths place. There's the tenths over here, and this is going to be the tenths over here. Okay. Okay, and so what's the difference between the two sides? The difference between the two sides is that one side is going to be rapid grow and one side is going to be better plant. So this side is going to be rapid grow and this side is going to be better plant. Okay, so rapid grow has 23.2, 23.2. So I'm going to put a 2 there. Okay, as one of those I'm going to put a 2. Okay, and then 23.5, I'm going to put a 5 there. Okay, so I gotta go out to the left, okay, in ascending order. Okay, and then 24.6 for better grow. We'll just continue with better grow here. It's 24.6. That's the only 24. 25.9. And then another 25.9. So we have 2 nines there. 26.0. Okay, for the 26.0. And then I've got a 30.1 down here. Okay. Okay, what about better plant? Well, this is just going to be like a regular stem and leaf plot. The stems are the ones, okay, 23 ones there. And then the tenth is going to be the 0.5. So that's 5 for 23. What about 24? 24.7, 25.8, 25.9, 27.3, 27.9, 28.3, and 29.1. Okay, extended or expanded stem plots. Let's look at this one here. This will be our last example. Sometimes there are many values with the same stem. So we like to split up the stems in half. The first stem has the following digits 0 to 4. The second has the digits 5 through 9. Okay. So if we split these up, okay, I would have to first order these or at least look at what are the stems going to be here. The stems looks like they're all in the 50s, 60s, and 70s. So if I do 5 and then 0 to 4, 5 through 9, okay, as my ones. So my stems are going to be my tens, and my leaves are going to be my ones. So I'm going to have a 5 and a 5, a 6 and a 6, and a 7 and a 7. Okay, so we can have the first five represent 50 through 54. 50 through 54. So let's see, are there any 50 through 54s? Okay, it doesn't look like that. What are my 50s here? My 50s are 59, 58, and 58. So so there's no 50 through 54s. Are there 55 through 59s? Yes, absolutely. There's 3 of them. There's a 58, a 58, and a 59. And I want to put these in order, these in ascending order here. Okay, 8, 8, and 9. Okay, what about my 60s here? Are there any 61 through 64s? Well, yeah, let's try to pick those out here. I've got a 61. Okay, let me erase my other circles. I'm done with those. 61, 62, 62, 62. I've got a 60. Look at that. Okay, and I've got a 64 and then another 62. Okay, 66 does not fit. 68 does not fit. 67 does not fit. Okay, and the 66 down here does not fit. Okay, so let's see what we got. And let's order these in order. I've got a 60. So that's 0, 60 there. I've got a 64. No, we want to do 61 next. 61. Okay, 62. I've got 3 of those. Okay. I'm going to cross up the 50s as well because we did those already as well. Okay. And so what am I left with? 60. Oh, did I do 3? No, there's 4 62s. Wow, there's a lot of 62s there. There's 4 62s. Okay, and then 1 64 at the very end here. Okay, so now let's do the other 60s. That's the 65 through 69. Well, I've got 66, 67, and 68. 66, 67, 68. Okay, so 66, 67, 68. Boom. 1, 2, 3, gone. Oh, and I had another 67 down here. So I actually had 2 67s, a 66, sorry, 2 66s, a 67, and a 68. Okay, what about 71 through 70 through 74? Well, I've got 4 of those. 1, 2, 3, 4. I got 2 71s and 2 72s. Okay, what about the last one here? We got a 75 and we have a 78. 75 and a 78. Boom, boom, done. Okay, so that's how we do the extended or expanded stem plot. Okay, thank you for joining me, and I'll see you in the next video.